Hello, welcome to Security, Cryptography, whatever. I'm Deirdre.
I'm David.
I guess I'm Thomas.
And our special guest today is Nate Lawson of Root Labs. Hi, Nate.
Hey, how's everyone doing?
Good. We're just going to jump into the conversation we were having before we clicked our button, which was you asking Thomas how he got into crypto.
Absolutely. Yeah, I had been talking to him about crypto in I think the late 90s, maybe early 2000s, and he never honestly seemed that interested. So I was wondering what changed in the mid 2000s when suddenly he started blogging about it and getting very interested in it.
Now he's a coastal elite podcaster.
It's true. That's how these things work. I forget how young I was back then, but at every point in my entire career, back to when I was working at 19 years old, right? I felt like I knew absolutely everything, not about everything, but about my own career. Whatever it was I was doing, I felt maximally competent at that thing. So I would have defined myself back then as I do practical security. Literally, these are the words I would use. I would say I do practical security, which I would define as all the security that is not cryptography. Which is impractical security, right? Where the back and forth of how vulnerabilities and stuff worked in there. Oh, I found this crazy cryptanalytic attack against a cipher and reduced the key strength from 128 bits to 112 bits, and I call it a day, right? That's kind of what I felt about cryptography. The simple answer is just pig ignorance, right? So I'm sure it was a Modesano project I was on, and I'm sure it was the result of talking to you on IM about what I had run into, and I'm sure it was that you had given me some kind of tip. It might have been SRP. It was probably SRP. It was probably, here's an SRP implementation. If you send it 0 instead of, the actual authenticator, you can log it as anybody. And then it actually worked. It's one of those imprinting moments, right? It's also the first time I ever did a web application penetration test. One of the first things I did, I didn't know how cross-site scripting worked or SQL injection worked. I was a memory corruption, vulnerability researcher prior to that. Or Unix privilege escalation and stuff like that, but none of the web stuff. And the very first thing I did on that project was I logged in as quote or quote equals quote. And it worked. Which ruined me for every other project I was ever on, because it set the expectation that happens normally. Somebody might actually have a SQL lookup in the login thing that'll give me SQL injection when I try to log in with quote or quote equals quote. The SRP thing is kind of similar, right? That bug almost ruined me for cryptography, right? Because there aren't many better bugs than that. So I think that's what it was. I think it was you telling me about SRP, and then just the realization that so my priors for crypto stuff was that the vulnerabilities were all impractical, hyper mathematic, and on a project, or if I was just trying to break into something, it wasn't going to give me anything I cared about. And then after that, it's oh shit, what else is there that's like this? And then you just gave me all my attacks. And that's how it happened.
Well, I think the key thing about crypto that I've used before as a catchphrase is that it's very strong, but also brittle. And I think that's what you got caught in, or could have been caught in where you were impressed by the potential strength of cryptography, but you hadn't thought much about the brittleness, about how it can all fall apart if you don't get it exactly right.
Yeah. How did you end up doing this?
That's a good question. Yeah. I was working for ISS in 1996, and I created the first network intrusion detection system, at least the first commercial one that I know of. And I was also young at the time, and was interested in the idea of this kind of empowering technology where a single network administrator could monitor a bunch of streams things that are going on the network, get alerts when things are going bad, and then intrude on the attackers and block them. Kind of thought of this augmentation kind of approach. And at the time I was enjoying that, but I was really dismayed at the state of security in general, bug track and exploitation, race conditions, and memory corruption. It was just everywhere. And basically attackers were winning. And so I wanted to move to an area of security where you could make stronger guarantees about what you had done. And cryptography was very appealing. The very first cryptography book I read was a library book I got when I was a kid And it had, classical ciphers, substitution, kind where you wrap a piece of paper around a pencil and, you write your letters on that, those kinds of things. And I left it on the swing set and it got sprinklers on it. So I had to buy it from the library. But that was sort of my introduction to cryptography. But yeah, like in 1996, I was looking what to do next after ISS, and I wanted to move on. So cryptography was really interesting to me. And actually, a mutual friend that was I knew on IRC said, "Hey, come out to San Francisco. I've got this interesting startup." And the company is called Simple Access. They were using Lisp to do some kind of like pricing prediction thing for e-commerce. And I didn't understand it at all. But I came out to San Francisco, had an interview in the Flatiron building, and was impressed, but also confused with the company. And my friend's like, I think that wasn't quite the right position for you, but there's this company near your school at Cal Poly SLO, and it's called InfoGuard, and they're doing cryptography, and you might be good for that. And I said, okay, I don't have any formal training in cryptography, but I'm interested in it. So I went and interviewed there, and I got a job. So InfoGuard was really interesting at the time. It was founded by 3 TRW people, ex-TRW. One was focused on like physical security. So he went to museums and helped them configure their sensors for alarm systems to test those kinds of things. Another was a cryptographer from NSA. And the third one was just kind of a manager. And the 3 of them had actually helped author the FIPS 140 standard, which was brand new at the time. Like it wasn't even really released. Yeah. Yeah. And their idea was like the cryptography, they created a fax encryption device at TRW. And they decided, along with NIST, that there needed to be some kind of standard for the actual implementation of cryptography and cryptographic protocols to make sure they're secure. And that way the government purchasing could ask for the certification. But what was interesting at the beginning, as I started working there, was that they were very focused on actually making implementations robust. FIPS 140 became a little bit of a joke later on when people are sort of rubber stamping implementations, running a few test vectors through and saying you're done. But at the time, they were really pushing for the standard to be like the minimum, and then certifications to be based on top of that, based on the creativity of the person who's doing the evaluation. So the first thing I worked on there was Netscape's SSL module.
Oh my.
Yeah. So Netscape had NSS.
God, you're like the Forrest Gump of applied cryptography. You're just popping up in like the past 30 years that you've been alive and working and all the cryptography. Sorry, Netscape SSL.
I've seen a lot.
I've given a few presentations that begin with kind of like Netscape SSL as a historical note, and then we go from there.
It's fascinating. At the time, it was SSL v2. And they had the NSS crypto layer. For the Netscape version 4 browser, they were working on adding a FIPS mode. They wanted to get government contracts to have governments purchasing their browser. And V3 was in process. And little bookmark there, Paul Kocher, who is the author of the SSL v3 spec, was working as a consultant at Netscape at the same time I was working on this review, but I didn't know it at the time. So for this FIPS module, we were kind of saying like, what would be the security boundary of this software? How do we? It had some non-standard crypto, like it used an MD5 based PRNG. So how do we certify this if it's NIST, which doesn't allow MD5 use? They didn't want to throw out the MD5. They didn't want to use SHA-1 instead, but which would have been allowed. So it's kind of a weird thing there. But also like, where do you draw the boundary? How do you in software, like is this crypto module going to have some kind of process isolation from the rest of the browser? You know, the keys it has, the keys can be like encrypted on disk. And so they had this thing where you'd enter a password in and it would unlock the keys, and there's just a master password which would do a key derivation. But that was trying to make it map to physical crypto modules, which is what FIPS 140 was focused on mostly.
Okay.
That was fun. I got to drive up to, Mountain View and go to the Netscape building there and talk with people there while they were working like crazy on this thing and try to get it done.
Where was the Netscape building, and does it still exist, and is there another company there?
Yeah, it's in Mountain View. I don't know the company.
I was going to say, is it the Firefox building now?
It was, I think Google took over it at one point. I don't know for sure.
That feels spiritually correct.
So first of all, you've got no cryptographic training going into InfraGard, and your first project is probably the highest profile piece of cryptography on the internet, which is great. You have a CS background. You were at Cal Poly SLO, but like, did you do like a lot of mathematics? Like, was math a big part of your CS degree when you were there?
I've never been that great at math, honestly. Like, when people program things, I think they often fall back on one of two mental models. One of them is language model, and the other one's mathematical models. I've always been the language model kind of person. So my superpower, if I were to pick one, is I can read a bunch of stuff, remember all of it, and then put it all back together by remembering it all. And so we had a great library at school, and I read every book we had on the history of computer security, all the way back to Rainbow Book and all that stuff. I read, old early DARPA papers about this stuff. A bunch of the early development papers around Lucifer cipher and DES and all this stuff. They had the differential cryptanalysis book by Ellie Beam, and so that kind of stuff. So I like just read all this stuff and remembered it all, and then and then I think when I got to InfraGard, I started reading all of the source code to all this stuff, that the projects they had done previously, and so I kind of learned it that way. And then the guy Ken, who was the ex-NSA person, was really helpful in helping me calibrate some of my mental models of these things about what's practical and what's not. And he had probably the best skeptical view of cryptography that I'd ever seen. And so we went
because he was breaking it all the time, or
yeah, and designing it. He was kind of a ham radio person, and so he was really focused on sort of cryptanalysis of broadcast communications and that kind of thing.
Got it.
So but he had a really good hunch for how to break things, and I absorbed that through osmosis and started kind of projecting forward what that would look like in the software world.
So you're coming from ISS, which like I think we're the old two people on this podcast, and Deirdre and David are the younger two. But like ISS and secure networks, I'd say, are like it's kind of like the birthplace of modern commercial vulnerability research. Is probably the way I'd put it. Right?
Pepsi.
We're the Coke and Pepsi of commercially looking for vulnerabilities. So like you're steeped in this culture of, you're reading all these books and stuff, but just knowing you somewhat socially before this is, I remember you being at InfraGard, and I remember, being warm acquaintances back then. So like I knew you when you were doing that, right? But I knew you long before that. So you'd been doing, commercial vulnerability research and, amateur vulnerability research, whatever we want to call it, right? For kind of like years prior, like you're like that's definitely, I would assume that's like just part of your mental model. It's just like, the way people look at systems and break them apart and look for flaws in the reasoning and all that, like just every vulnerability researcher does. Did that like carry over to the cryptography work that you were doing when you were reading stuff? Were you like reading it adversarially? I'm really curious about like, I have an idea of like roughly your level of, I don't know what the word is, but like your comfort level breaking crypto systems now. And I have no idea where you felt like you were in 96 or whatever when you started at InfraGard, right? Like how would you say you're different now than you were then? Like what would you have done differently on that project?
That's a lot of questions. The first answer is that, yes, you look at it the same way you look at attacking any system, identifying different vantage points an attacker can have, how they can get to those vantage points, what leverage they have over the system from those vantage points. One of the interesting things at the time I read was about how to prove protocols correct. And that was a really helpful thing because it forces you to describe and write out all the different capabilities an attacker have. Can they change a value? Can they learn a value from a certain vantage point or after they've seen certain messages? And that model applies to an entire system. So if you look at like a PRNG, can an attacker choose entropy going into the system? And if they know entropy, like partial entropy exposure of the PRNG state, what can that allow them to do? And I gave a really short rump session talk at Crypto 98, I think it was 97 on this. It was really, really early. I think it got recorded, but it was like one of the very first recorded ones. But I was talking about how, I think it was the SSH PRNG I was talking about, but there's the mixing process, there's input entropy, and I was discussing about the different ways an attacker can either partially control or influence the entropy pool. And so when most people thought about entropy, they thought of it on the output side of like, how much entropy did you feed in and how much did you get out the other side and how far can you extend that securely?
Yeah.
But not as many people were focused on like, okay, now you've had a partial exposure, you know, half the pool. What about this particular construction of how it's mixed? And how long can you maintain partial or full knowledge of the pool after that point? And so again, that's just kind of that thorough vantage point model for looking at attacks. But what was your second question?
Yeah, I lost my window because I was in archive.org trying to find a working version of the video link for Nate's 98 crypto talk.
I can look it up later.
I guess like, you know, a general thing I just wonder about the kind of like the FIPS verification type work that you were doing at InfraGard, because like your career kind of rapidly goes into more high end, you know, kind of cryptanalysis or whatever we want to call crypto vulnerability research and design too. I mean, you're actually a, you know, cryptography engineer where I'm like a vulnerability researcher / crypto gadfly, right? Like David and Deirdre are both actual cryptography engineers, right? But like you kind of rapidly got into actual pretty serious, like, you know, breaking systems and stuff, right? Because you moved on from there to, you know, cryptography research, right? So I guess I'm curious, like, you know, was it kind of like checkboxy stuff? Like this system, like here's reasons why this system isn't sound, but we're not going to go into the details of like what you could actually do with it? Or like, did you actually have findings on those projects that you'd like consider like now actual vulnerability findings?
Yeah, that was really interesting. The companies would definitely, when they're being evaluated for FIPS 140, they definitely push for a rapid certification. And they'd argue whenever you found something that they said was outside of the guidelines. You know, it'd be like, well, that's not allowed because the crypto boundary is here and that's it over here. And it's like, yeah, but that does influence the inputs or outputs of the system in a way that gives an attacker some additional leverage. So no, we can't leave that out. And my managers would go to bat for me on this, so which is great. Yeah. It was the company culture was like, we need to secure this stuff, and FIPS 140 is more of a guideline. Yes, we need to make sure we've checked all the boxes, but in addition to that, we need to explain or fix anything we find. And but the companies definitely had pressure to get certified because it was getting in the way of their purchasing with the U.S. government. So it was a tough dynamic, and one which I think ultimately undid the usefulness of FIPS 140. But early on, it was seeming like we were holding the line on this. There were a lot of things which were necessary because of the design constraints at the time, the technology or the gate equivalents or whatever you could get out of a design, power issues that necessarily limited it. I worked on a crypto radio for Motorola at the time. And one of the things was the PRNG for how it did keying for channel communications. Mm-hmm. And it's hard to get entropy when you're wandering around a battlefield with a radio on your back. And they didn't have room for like a lot of NVRAM or anything like that. So it would like open the microphone, push the gain way up, and just hash together a bunch of noise.
I was going to say, I was trying to think of how you would do that. And I'm like, I have a comparable supercomputer full of sensors in my pocket right now. I'm like, accelerometer, like just see some accelerometer crap. And I'm like, oh, you don't have that. Like, what do you have? It's like, you have a mic or you have the antenna. So yeah. Okay.
Yeah. And so we tried to do things like keep some state from the prior communication if there was one. So at least you weren't starting completely from scratch, but a lot of times you had to bootstrap this, and you can't really make strong guarantees about how much entropy you have in that before you use the first key. And that was a critical environment. Ultimately not very solvable with the equipment at the time. One interesting thing that happened as well was, IBM had this giant mainframe, the S390, and they were building this crypto processor. And this was going to be the first level 4 FIPS 140 evaluation. They really wanted to go to the highest level. And this thing was giant. It's probably the size of a dinner plate. And it was a chunk of metal, steel, maybe about the size of a dinner plate, shoebox or something like that. And it went in this mainframe, and it's going to be used for deriving pins for ATMs or whatever. But they wanted to make sure it had, like, at level 4, you have active tamper resistance. Oh. So it had like a battery inside and an envelope around the whole thing and epoxy potting for all of that.
Oh, wow.
Yeah. And I think it generated a lot of heat as well. But anyway, they were like, we want level 4 evaluation. We're like, okay, we're going to like really work on this thing. We're not going to give the first level 4 of the entire program to something that we haven't really hammered on. Just because you say you have an envelope doesn't mean that's enough. And so the physical security guy, he x-rayed it and a bunch of stuff. And it was kind of interesting because of the way they had mesh, and the mesh was inside the epoxy, but the way the mesh was folded, it's a flat sheet. And think of wrapping a gift.
Yeah.
You kind of fold things, but at the corners, you have multiple layers that kind of meet at the corners. And by x-raying it, he found there was like the tiniest of creases sort of at the corner where they fold it. So he got like a dentist drill and like drilled through the epoxy into it and hooked like, like a really tiny hair thin wire to it and added power to the mesh, and then was able to cut away the rest of it without zeroizing anything.
Wow.
And there was like, uproar over this because that's not part of the blah, blah, blah. And standard, and like, well, it needs to resist, this kind of attack. And this was a pretty straightforward attack. So, they did some changes to their production line or something like that to address that. But yeah, that really revealed the kind of conflict in trying to reach some of these really high security levels.
With the stuff that was going on, or like in the mid 90s, then especially with SSL 2 and 3, like how much did the export restrictions come into play? Because like that was a big part of SSL, and like rediscovering how that worked was like, and then turning it into vulnerabilities like 20 years later is what qualified me for a PhD. But like, if you told me like, oh, we already knew all that in like the mid 90s, and just that was kind of the way the world was, and then we rediscovered it in 20 years later, I totally believe you. And so I'm curious if there was like effects from the export regulation beyond SSL v2, or what dealing with that was like at the time. Yeah,
that's really interesting. Yeah, we were, for these products we evaluated, we were definitely pushing for triple DES as kind of the standard block cipher mode, or block cipher, I mean. But a lot of single DES products were still coming through. And I mean, back when the original DES was being certified, or standardized, they definitely had debates over to the 56-bit keys and why do we need these parity bits and crap like that. And people knew it was going to be insecure from that. But at the time, DES was also being designed more as a hardware algorithm, and software implementations were possible, but most people didn't think it would be used in software because it was so slow. We're talking late 70s here. So. Oh, okay. Yeah. So people were thinking that we want something that's simple to implement in hardware and small gate-wise. Mm-hmm. And so they're like, well, 56 bits would probably be okay, even though it's not great. Cryptographers, of course, didn't say that, but the engineers who were building the systems based on it were like, nobody's gonna be able to brute force search 56 bits for a really long time. But by the mid 90s, there was the Clipper chip debate going on. Yep. There was a lot of like key escrow stuff was finally becoming a national issue, and the NSA had been sort of flexing their muscles around interfering with designs of various systems. Not ones I worked on directly that I know of, but just in the background, contacting people who had worked there before and saying, you should really modify this. There were some rumors about some of the cryptographic, the telephone encryption devices and things like that at the time from different companies, and just like what kinds of additional little backdoors they had added to them or whatever. And that was definitely very prevalent. In terms of SSL, the export modes were a really big deal. In fact, I don't remember exactly how it worked, but I think you had to download a different version of Netscape to get the non-export modes. And you had to like certify something or on a web page or something. I don't remember exactly, like you're not a controlled location or something. Yeah, ITAR, etc. My understanding is they had the US version and the international edition, and you just had to like pick the right one to download when you like. It wasn't hard. Yeah, it wasn't like there was a hard restriction there, but they had to do something to differentiate their builds of that. And I think they didn't it also have like 40-bit keys. RC440, I think, was one of the minimum cipher modes, and besides none. Yeah, I believe so. Yeah. So that was even worse than 56 bits. But yeah, in FIPS mode, all that was disabled. You couldn't use anything less than single DES, and triple DES, I think, was the preferred mode if the server supported it. So at that time, we were already trying to push for, because we knew it was totally insecure. But I think that did limit a lot of the things that manufacturers were designing. They were always there was always a consideration in what they were creating.
Mm-hmm. I'm going to bounce back to what I was asking before, and I'll ask a more direct version of the question. First serious, like I would have considered it a serious crypto vulnerability finding. Roughly what was it?
Good question. Would this be like the first time anyone discovered something and published it?
First time you were able to either find or use something on a project. What was your SRP moment?
Let's see. It's a good question.
I'm investigative reporting. We're uncovering the fact that Nate Lawson has never discovered a crypto vulnerability.
No, I have.
Of course he has.
No, the reason why I'm hesitant about this is I definitely have done a lot of design reviews, and that was the earliest stuff I was doing. So it was, the question is, most of those cases, I'd report it to the company and they'd fix it. It wasn't, there's no exploit needed. So, when I was working for InfoGuard, there was a lot of cases where he said, you need to change this design. This key material isn't being encrypted before it's written to disk. It's written in plain text here. And like, well, no one has access to your plain text unless you're on your machine already. And that kind of thing. There was some of that. The stuff I talked about with the PRNG mixing, sort of not thoroughly mixing the entropy, or the entropy mixing happening only periodically, so that there were times when raw entropy would be output from the pool. There was cases like that.
Ooh.
Yeah. I mean, the first one that I found that I don't think anyone had published this specific thing before, and they didn't actually publish it, but before the Xbox 360 HMAC timing attack, I had privately found HMAC timing attacks in other systems that we were reviewing and put it in a report. That was kind of the first one, I think. I mean, everyone knew about timing attacks at the time, and people knew like the secret key material associated with HMAC, for example, was sensitive. But I don't think people realized that the HMAC of a specific chosen value is also sensitive. And so being able to do a timing attack against the HMAC comparison, where the victim has knows the correct answer as well as your guess, and that could allow you to iteratively guess what the correct answer is. I think that was the first one of that specific instance. But again, it was like I was specializing something that someone else had already invented.
On the Xbox 360, is that what the mod chips that you would buy would do? Were they executing an HMAC timing attack?
No.
Or was that just like, we have connected to the debug ports, like, screw you type?
There were a number of interesting flaws in the Xbox 360. One of them was a hypervisor attack that was kind of interesting, where they found a syscall that wasn't validating its inputs properly or something like that. And they were able to get software code execution. The earliest attacks were swap attacks against the CD-ROM. And that was kind of interesting. Well, so it depending on the system, versus, the PlayStation 3, the Xbox 360 had earlier attacks against like copying the discs and DVD-based attacks, and without the whole system security being broken. Whereas the PS3 sort of stood up longer, but then, had fail overflow and a total like compromise due to ECDSA repeated nonsense.
I remember that one.
Which is like a classic.
I've always had like a kind of special spot for that kind of stuff, because like I started kind of getting into some of this stuff in high school in the context of like being, to make you guys feel old, like in the mid 2000s, being a user of like the buffer overflow exploit on the first Xbox to be able to run like Xbox Media Center and other stuff, and then also play pirated games because I was in high school and didn't have any money. And then that eventually turned into getting the mod chips for the 360. And then like some years later, in like undergrad, I was like, oh, that's what a buffer overflow is. And like, oh, these are the bytes like on the like all the like networking I put together to like be able to stream like 480p TV to the Xbox, and like setting up Windows file sharing. Oh, this is how all this stuff actually works on the wire.
I was such a little media pirate in high school, but I didn't know shit about cryptography or even security. I just knew that I had to get around some stuff. And like, I didn't even go very far. And I wish I could go back in time and tell high school me, like, psst, like run this little script. It's fine. And it works with a little bit of math, because I just had no clue at the time. I was a little bit motivated, but I had no clue. Do we want to go into like crypto then versus crypto now? I'm kind of curious about this.
Well, I wanted to address something that he said first. I think that Thomas has actually done more attacking cryptography stuff than I have.
Not a chance.
I've done a lot of in terms of exploiting it. So I've done a lot of auditing of designs, and I've done a lot of designs.
I've repeated the same dumb attacks over and over more than you have, but
and they still
maybe.
work.
But you have a broader,
in terms of
broader variance of attacks that you're able to deploy.
I'm sure you've exploited many more systems using cryptography than I have. And the thing is that I did a lot of design reviews. And again, like when you do a design review and you find something like, oh, this system doesn't verify the RSA PKCS padding. It's like, well, what can you do with that? And, when I worked with Paul Kocher at Cryptography Research, he was the one that found the exact sequence of papers. They're like, okay, if you have an E equals 17 RSA system and, you're not verifying the signature padding, it takes approximately this number of queries to be able to forge a signature and that kind of thing.
You could do that attack with E17?
With a lot more queries. Yeah, but it's feasible. Yeah, I can't say what the system was, but there was a piece of hardware that had an E equals 17 RSA implementation, and they didn't verify the PKCS padding on the signature of something that was very important. And so you could do the same attack you did with E equals 3 that became public in 2006. But it took a lot more queries. I can't remember exactly how many, but let's say, a million queries. But this is hardware you have physical access to, so you can do as many as you want.
I feel like, I can mentally run through the basic attack. I've got attacks that I didn't directly get from you, but they're all kind of stemming to you. And then I've talked to people that are kind of in the field now and doing lots of work that are in the field now because of blog posts and stuff that we wrote. So your influence, Tai Duong is a good example of somebody who's you've indirectly, more or less directly, because I don't do anything that doesn't parrot you, kind of influence that whole line of TLS attacks and stuff like that. Right. But I'm kind of obsessed with, I'm imprinted on the idea of bug classes, right? It's the way my brain was wired from being a teenager on, Pound Hack IRC and the currency value of a new kind of exploit that's repeatable in other pieces of software, right? There's the lowest level of people doing, dumb hacking stuff where they're just trading scripts. And then just one level above that is you understand how the script works. And if you had a source tree, you could find that same bug in something else and then have a 0-day bug, right? So I'm kind of that's as far as I go intellectually into this whole thing. And I'm obsessed with that stuff, right? So I feel like you taught me the CBC, bit flip modification thing, which we used on a project to there was a CBC encrypted stream and we were able to bit flip admin equals true into it. Which again, another high payoff attack, right? We did the you're just talking about it just now, the E3 PKCS signature thing. So that's Mozilla was shipping with, there are still tons of E equals 3 RSA certs out there. And Mozilla is shipping with an implementation of, certificate signature checking that doesn't check all the padding bits. It just decodes the padding, extracts the hash, and then compares the hash. And we wrote a whole series of blog posts about how exploitable that is, right? Essentially, you can build the signature you want and cube root it essentially, and get a valid signature, right? So that's another example of a bug class. And I've weirdly enough, I've also found that on some pretty high profile projects. It's almost the higher profile the cryptography is, especially if it's embedded, or in some piece of software that's impossible to get a spec for and very difficult to reverse. The more important it is, the less likely it is that somebody's actually done serious analysis on it. Just basically compared it to the literature. The SRP one is another example. A lot of those attacks are you can't have them so much today because we just don't use crypto primitives that have these problems anymore. So I am kind of curious, how much of what you were doing at Cryptography Research or even in the 1990s carries over to things you'd actually find in a modern system where they're using, it's an authenticated key exchange with curve 25519 and, authenticated cipher. And that's pretty much the end of it, right? You were kind of doing this stuff a long time before, I was, right? And I will not shut up about the IETF mailing list stuff about IPsec and people talking about how they're setting the IVs for things and Phil Rogoway coming in there waving his arms screaming, "Don't do this," recruiting every other cryptographer in the world to do open letters to the IETF, and it's still happening.
Yeah.
So I don't know if there are non-obvious ways that cryptography is different now than it was then.
I think there are some clear ways. I mean, I was a big fan of the work that Dan Bernstein did to help eliminate certain bug classes from his both his ciphers as well as some of the ways he uses ciphers, to do things like making the key identity part of the key, for example. So it's not just an untyped set of random bits that people did before.
Yeah.
I compare it roughly to like type enforcement becoming part of languages,
Nice.
and not using type safety in your programming as being a problem.
Yeah.
I mean, one of the reasons why I was so focused on design reviews and design from the early stage was because things were so bad. It was like, there's no money really in exploiting anything. Like the money to be made as a consultant was on the design side, and there was the systems that were using cryptography were like banks doing PIN derivations with really boring kind of janky protocols for that, using DES and stuff like that. SSL itself was just there to convince your family to put their credit cards into the internet. And that's why it was created in the first place. So like all these things are really boring, honestly, in terms of like even if you had an SSL break, you would scare people not to put their credit cards into web pages for a little while. I mean, it was like, what's the real impact on society from that kind of thing, or hardening it so that it's more secure? So there just wasn't much value in any of that stuff, or impact. But in terms of where crypto mattered, it was kind of the military communications or things like that. And I didn't want to work for the government.
Mm-hmm.
So being on the periphery of that, and then once the internet started taking off and started getting more mature in the early 2000s, it started getting more interesting to actually protect communications, and devices more widely started adopting cryptography. You had, early Palm pilots or things like that. And
Blackberries.
for Blackberries, all this stuff like that. There's devices, game consoles started adding interesting copy protection to them.
Yeah.
And so there's just like crypto started creeping into so many different areas, and it started actually getting interesting. So I think that like the difference between the late 90s and the early 2000s, the biggest difference was the crypto was super brittle back in the late 90s. It would fall apart if you looked at it wrong. And that was almost not interesting because there were so many ways it could fail. And then by the 2000s, the platforms are starting to get more secure, and people were starting to rely on it for more interesting things.
Mm-hmm.
And so they started coming up with more interesting protocols. I mean, pairings and identity-based encryption, all this stuff started appearing, in the mid 2000s. And maybe that itself didn't change the world, but nobody even cared about something like SRP back then.
We have all these whiz-bang zero knowledge proof systems now because we had pairings. We wouldn't have gotten to the places where we have them without pairings, without first having the pairings first to actually make them make my snark a little, 500 byte blob that I can throw. I can throw it on a TLS connection now because I can have zero knowledge proof enforcement middle boxes and crap like that, or I can put it on a blockchain. You said that like the cryptographic protocols that we had in the late 90s would fall apart if you looked at them wrong, and now we basically don't have that anymore. Like what parts of the designs of how we're putting together, I don't know, cipher modes or asymmetric protocols makes it so they don't fall apart when you look at them wrong now?
So people, are actually focused on doing proofs, which at the time people just hand waved and said, I can't do proofs. SSL v3 has a clever hack to prevent downgrade attacks to v2, where there's the version of the SSL protocol gets stuffed in the padding for the key exchange. And Paul came up with that as a clever way of just like, okay, I don't have any other bits free in this backwards compatible protocol, so I'll stick the message there, and then hopefully so it's not malleable. Someone can control RSA in various ways.
And now that's like a well-known you wouldn't put it in the padding, but you put it in the transcript and you hash in the transcript somewhere at the very end.
Absolutely. And that's a much more solid design approach. And I'm not criticizing that hack. It was necessary to make it backwards compatible with protocol that was already out there and fielded. So it was clever. People are more careful about proofs, about including all the meanings of the things they're hashing together, not just the things themselves. Like I hash 3 keys together and I get a value. It's like, no, I hash the intent of each key and the key usage bits and the maybe even the state of prior messages and those kinds of things. HMAC didn't exist until 97, I believe. And so we were doing arbitrary hash constructions to try to approximate HMAC before realizing what we needed there.
Yeah.
So like just simple things like that, but also side channel attacks. The first timing attack on RSA, Paul published in 96, I think. and then differential power analysis in 98 or 9. I don't remember exactly, but like side channel attacks weren't really a thing. You know, people talk about Tempest, at the time, and it's like, oh, well, I can't see your screen by analyzing the emissions. Then I guess there's nothing more to be done, or it's just all noise. But like nowadays, people design hardware, they design protocols to be side channel resistant. Even the cryptographic primitives making non-data dependent rotations or things like that as a primitive for block ciphers, stream ciphers.
Yeah.
There's new things like lattices and lattice-based crypto, which I was super skeptical about.
Well,
so
okay.
my sorry, go ahead. This is in your expertise now.
Well, so we kind of talked about how, like, you would look at it wrong, it would fall apart, and Thomas was saying like, oh, all these like classes of attacks that either the ones that were happening in the 90s aren't you don't have to worry about them anymore, but Thomas has done a lot on like classes of attacks against elliptic curve based protocols, like small subgroup attacks and things like that. We're coming up with a bunch of lattice-based stuff. Like there's lattice-based, key establishment. There's lattice-based signatures. There's lattice-based zero-knowledge proofs. There's fully homomorphic encryption. And I wonder what the next class of attack.
I'm very excited about this.
And like, I don't know what it is yet, but I know of one of them. And for all of these key establishment exchange mechanisms in the NIST competition, they put them all into this chem. It's not it's not key exchange. It's like key encapsulation. And all of them, except maybe one, I don't know if it was all of them, but maybe all but one, you have to do this transform, this Fujisaki-Osaki transform, to turn it into a chem. And all of the submissions to NIST did it wrong. There was a bug, there was a vulnerability in it, and everyone just did it the same way. And so I'm just sort of like, that's not even a lattice thing, but that's like a whole new thing that everyone had to do, and they all did it wrong, and they were all vulnerable to the same leak or, downgrade in security. Do you see like new classes of attacks coming because of this post-quantum stuff? Or there's sort of things that are so like, I hope we don't forget the lessons that we learned in the 90s and the past 2 decades when we're doing all these new post-quantum crypto systems.
Absolutely. Yeah. You're way beyond me in terms of post-quantum. I'm not up on the latest of any of that stuff. But back then at, Crypto 97, I think it was when Intru first came out.
Yeah.
And my team and I were super suspicious of it. We're like, lattices are great for attacking things, and they're super linear and all these kinds of things. This is a shaky ground to build something on. This is crazy, And a lot's changed, but a lot hasn't changed in that. And lattices are still good for using integer lattices, useful for attacking various crypto systems. And their usefulness as a cryptographic primitive is still not, in my mind, still not completely proven. And the meta thing that certainly no one should forget is anytime you shift between a well-known set of primitives that you build things on with well understood limitations, you're going to have big potholes that appear that you didn't know about. Mm-hmm. And sometimes those can be coded around or special cased or whatever, and sometimes you can't. So I'm speaking very generally, like I don't know anything about post-quantum systems, but that shift. And of course, as you mentioned, the implementation problems and classes of implementation problems always appear whenever you have a big shift as well. I see a similar thing happening with like speculative execution and those kinds of side channel attacks where it's like, okay, everyone's known microarchitectural side channels have been an issue, early 2000s, cache chiming attacks, branch target buffer, et cetera. But they haven't really understood all the interactions of the microarchitectural state. And, what if you got something in branch target buffer and in some LRU list for return calculation or whatever? Like processor is so complicated these days that there's going to be emergent behavior of all kinds of these things. And there's going to be emergent behavior that builds on emergent behavior. And some brilliant person someday will find some attacks in that.
It's like a hell of a second act for Paul Kocher.
Yeah, absolutely. Yeah. He was always, when we were working on these systems, a lot of his work and my work with him was on smart cards. And smart cards are a very constrained system. And I'd argue they were one of the first important mass market uses of cryptography. besides software like browsers and things like that. They were around since the late 90s. You have EMV for payments and satellite TV with access control to pay TV and pay-per-view and channel encryption. And those two uses of smart cards were sort of the first mass market consumer interest in crypto in my mind. So Paul was working on those things very early, Paul and team there at Cryptography Research. But yeah, when you look at that today and people rebuilding from new primitives, it's like there's so many problems in this and so many ways that none of us have predicted it's going to come.
Yeah, like in the browser world, you mentioned, the SSL was built so that you could do e-commerce on the web. And then, you end up with PayPal and all that kind of stuff. One of the like earlier memories of like anything related to safety on the internet, I remember like my mom or dad saying like, if you ever buy anything online, like you should probably use PayPal. Not that I had any money or a credit card because I was like young, but like you have to look for the lock icon. Is like one of the first things I learned about like safety on the internet, besides like don't talk to strangers. This was before you ordered strangers to pick you up in your and drive you places on the internet. Yeah. But it was, really the exception instead of the norm. And then as things start to change, like you said, the problem of, how do I encrypt a few things for e-commerce versus like, how do I make the web encrypted by default? And then like, training nowadays tells you not to look at the lock icon. Like the lock icon is not an indicator of a site's trustworthiness or safety, or does not mean you should put your credit card in. You should just mostly ignore it as long as it doesn't say like insecure HTTP. And that whole trend has been, I don't know that I have anything to say on this other than like, that's where it started. And then the problem is now like, now I argue about like TLS and root certs for a living, right? And that's because we started with all the e-commerce stuff that you were talking about.
I have a good segue here. And my segue is we should find a way to talk about DRM.
Well, I mean, I've done a lot of work on some DRM systems like the Blu-ray crypto system, or Blu-ray protection system called BD+. Well, can we talk about satellite TV first?
Sure.
Okay. Well, so in terms of DRM, like the history of it, the earliest kind of DRM was, in my mind, was copy protection for floppies. There was also signal encryption for HBO and that kind of thing, pretty early on, scrambling things, and that led to cable and satellite TV encryption. And because there was real money behind protecting stuff, and you had to give access to the data to the consumer, that meant there's a lot of innovations in endpoint protection that started early on with smart cards and satellite TV and that kind of thing.
It seems like a very hard environment to do any computation when you're handing over some sort of way for the secret to decrypt or descramble to the adversary, quote unquote.
Yeah. And it was interesting because a lot of the trends that we saw in software cryptography and things like that later were foreshadowed in pay TV and the smart card industry for that. So yeah, early on it was kind of like obscurity. So there would just be descrambling routines and hardware and then eventually smart cards that computed that key and handed over to the unit to decrypt it. But it grew from there. And by the late 90s, there was a highly funded sort of gray market economy around this where people would hack smart cards and then people would build emulators for them. And then the channel data that was coming down was encrypted video and audio, but also had code updates.
Yep.
And so you had your smart card running code constantly, coming with little patches that were coming from the broadcaster. And so you had people doing things of like hashing memory, looking for patches to the firmware of the smart card to see if someone was reusing the card to siphon off keys. And then there was kind of a cat and mouse game going on with that. And that was pretty amazing. When I first interviewed at Cryptography Research in 99, Paul and Ben there were like, they had a satellite dish bolted to a board and had it stuck out the 8th floor window on Market Street in San Francisco to like get satellite access. And they were like analyzing as a consulting project, analyzing this smart card. And they were doing DPA on it and as it was deriving channel keys and stuff like that in order to figure out how it was working. Yeah. So that was one of the first, I think, hardware applications of DPA was satellite TV cards. And they parlayed that into a consulting project or design project, I should say, to improve the security of smart cards, because hackers were just breaking every single one as soon as it came out. I think the latest one at the time, they were able to, there was an ASIC on board that they weren't able to emulate perfectly. They didn't have the exact gate layout of it, the attackers didn't. But what they would do is they'd completely compromise the software and then just use it as a peripheral. And so they would run an emulator on a PC, and it would make calls into the smart card just to have it compute this extra little hash function, that was unique to the ASIC on the side. Mm-hmm. And one of the most amazing things I saw them do was, and again, I can't take any credit for this, I just saw it happen, but wasn't part of this one, but they used power analysis in order to reverse engineer custom instructions on a new ASIC that was being developed. So they actually were able to identify like the ALU and the shift operations and stuff like that just by looking at the power signatures, and we're able to feed in different inputs of encrypted instruction streams into this thing, and then they'd use the futures to be able to say, okay, this is kind of how this instruction operates, and then use that to fully reverse engineer and then emulate that chip.
That's wild.
And that was all done privately for the company, but it was pretty amazing. They had this software emulator for this thing that hadn't even been released yet in hardware. And they're like, okay, well, that's completely broken. So what do we do next? And they came up with a really amazing system that I have never seen anybody else do anything like it. They came up with software to design hardware. Okay. And that sounds like EDA, right? But it was software to design hardware using a PRNG. And so what it would do is they had a certain gate budget that was going to be on the next ASIC. And they explicitly said, no JTAG access to this part of the chip. We're not going to make it testable. It's testable sort of as a black box, but that's it. It has its own EEPROM behind this cryptographic primitive. But nobody else can access it directly. And then they seeded the PRNG by typing a bunch of garbage on a keyboard. And the PRNG would go and incrementally build up both a forward and a reverse function out of gates. And so just say, let's just take an XOR and then take these inputs and these outputs. It would randomly mix together the connections of it. And, you build up, 10,000 gates, 30,000 gates, whatever. And the forward function, the reverse function were different. And these were used as a component in a block cipher, as like a Feistel network. And so they designed the budget such that the most expensive FPGA you could buy on the market could just barely fit this whole thing. And it used up all the routing resources, and it was like $3,000 in FPGA for the encryption side of it on the head end. And then in the smart card had the decryption side of it. And so they'd run, and they worked on like characterizing these networks to make sure that they were balanced with linear and differential cryptanalysis characteristics and all these things. It would automatically analyze all this stuff. And then if it passed the tests, it would say, okay, I've got a candidate here. If it didn't, it would just start over with a new seed. And so what was amazing about this was it was designed such that they didn't actually know what went into the chip, because the customer took this software, ran it on their side, put in their own seed, and it spit out a netlist that we'd never seen. And they sent that into manufacturing. They test it to make sure it worked functionally. And there were some power issues because about half the gates were switching on every clock cycle. So it used a ton of power, but they were able to work on the power issues and make that all work. And that actually shipped in the early 2000s. And once that came out, the emulation attacks just stopped. Like the attackers were set up to do amazing micro probing of ASICs and be able to extract secrets from things and glitch stuff. And they were really, really good at all that. But I think the combination of this large, unglitchable 30,000 iterations hash function with random network of gates that, you have to kind of attack the whole thing at once. You can't really partition out parts of it and just ground a line here or pull the line high there or glitch a single line and have it do anything useful, because it would just come out with garbage and not derive the correct key if you did any of that stuff. Yeah. But it was an amazing thing to see them design that.
And it wasn't designed by a human. It wasn't compartmentalized into pieces and having some sort of applied logic to how the information is flowing through the unit. It's literally just gobbledygook until it passed all of these conformance tests, and then they're like, cool, ship it. So It's really hard to reverse engineer something that was not engineered in the first place. It was just like a randomized thing to find a conformant solution. And then, it's wild.
And it was used in a cryptographic way that they would encrypt channel keys with this, and the only cards could decrypt it. They could have different random functions for different families of cards. So maybe every 6 months you could just output a new mask design and, do some validation tests and then ship it again. And so you could do revocation based on that, or on key trees that were used for specific cards programmed into their EEPROM. And you could do smart stuff with like offline or partially online pay-per-view, where you could do like send a message to the card, say, okay, you can unlock this pay-per-view event of some boxing thing or whatever. And only certain cards could unlock that using that cryptographic value. And it would hash all this stuff together, generate a key, compare that to the current state of, say, a counter in the EEPROM behind this thing, and then only allow the counter to be decremented if it matched. And then once it was decremented, there would be a new completely random value, effectively random value, that you'd have to match for the next unlock. And so it was a really clever way of using cryptography to make it hard to do point attacks. I kind of describe this as like a mesh system where all the pieces hold together well. It's not like a long chain where breaking any link makes the chain fall apart. Each of these pieces is mutually reinforcing, and it made it so it was you'd have to have kind of a parallel attack, breaking a bunch of things all over to really make it useful.
Yeah. Which is in theory doable, but it's still harder. And it makes the bar for successful attack even higher.
Absolutely.
That's usually enough for a win.
Is that roughly how like these systems work now, or have we gotten to a point where you can like you have something closer to like an actual network connection between something in space and the thing at your house, and you just negotiate a secure channel and speak, separate data streams to everybody?
Yeah, I mean, these days I think that there still are some ongoing low-level attacks where someone will compromise a single box and then just redistribute the channel keys. And so if those get repeatedly taken offline because you just do trader tracing or whatever to find out what the box is and revoke that key. So there's things like that because they have to leak the channel keys to all their subscribers. But honestly, I think most of that's gone kind of into attacking streaming stuff like Netflix or whatever. And broadcast pay TV itself isn't quite a huge market anymore.
Yeah, I think satellite radio worked similar because I remember at some point there was growing up, my dad had a radio that for some reason just got free Sirius satellite radio until one day it didn't.
Yeah, that whole market was where, for example, broadcast encryption was developed for that, where you had a key tree and the ability to revoke subsets of that key tree at multiple levels. So you could say knock out this entire group, or knock out just one person in that group with a specific key. And doing that efficiently with small messages was where broadcast encryption was invented. But also zero knowledge proofs. This was sort of, I think, the first commercial application of zero knowledge proofs. There were some things like that were part of the early protocols. So yeah, it was interesting. To me, that was a very interesting industry because there was real value behind it. And there were very specific limitations of the systems. It's mostly one-way communication from broadcast from the head end to the actual consumers. And you could ship them updated smart cards in the mail that people would plug into their set-top boxes, when something got broken. So it's kind of renewable in that way. And so you had this creativity around broadcast encryption, zero knowledge, et cetera, to try to deal with the problem of people cracking it and making money off of that. You just didn't have that in the internet software.
It's interesting that they were doing like key trees back then, because I feel like trees of keys kind of became in vogue in like the internet world around like 2014-ish with the work from Joe Bonneau, whose name is escaping me, and then certificate transparency. And then what you were describing for revocation is exactly how like messaging layer security works now for group chats.
I was going to say, like, the tree chem stuff is like literally trying to pick this up to get the efficient a key agreement or availability of keys amongst like thousands of parties who are in a group or whatever. And this was apparently in vogue in a completely different area almost 20 years ago or more than 20 years ago. Wild.
Yeah, I think the first one I saw was for DVB, digital video broadcasting was the first one. I think one of the IBM researchers was the first person to do that.
So you were there for cryptography research, kind of doing, the analysis of like the satellite TV smart cards. But then you were like directly involved on the Blu-ray side of things. And I think like nobody cares about Blu-ray discs anymore. So like probably nobody thinks about DVD+.
I think a lot of boomers
like,
care about Blu-ray discs still.
HBO just took down like half of its shit after it got bought. So I have a new invigoration to re-up my Blu-ray collection.
But like the Blu-ray content protection system is kind of fascinating, right? Like how that actually works.
It was an interesting story. The history of that was that at Cryptography Research, we'd had a lot of connections with both the engineering side of things on satellite TV, but also Hollywood a little bit for the video. I actually ended up building one of the first digital projection systems, the storage encryption for that.
Yeah.
So there was a small company, it was all small companies, but there was a company that was going to like, for digital projection in theaters, was going to do the distribution of movies for that. And they're like, okay, we're going to use the internet for distribution. And, at the time the bandwidth just wasn't there. So we're like, okay, we're going to FedEx hard drives to theaters, and it's like, okay, well, we want to say we have the best security because this is like the highest quality content here. So we want Cryptography Research to design some crypto for that. So that was one of my first consulting projects at CRI, was helping the small little startup company. We built a storage encryption thing that was based off of SCSI, and you'd have a SCSI hard drive you'd plug in. It had hot plug, so you'd like plug it in and it would detect that there's this hard drive. And it'd be like, oh, I got an encrypted movie here. Do a handshake with a smart card that we had programmed. And just to like show how cool it was, you could also in your encryption, you could require an online handshake, and it would dial up with a modem over a cell phone and do this like secure handshake with a server to get part of the key material to derive the key for that thing. So it was kind of an interesting demo. I actually met Chris Coppola, who is the brother of Nick Cage. He was like,
is that a cryptographer?
Nope. he is a director of various movies, and the movie we had encrypted was a crazy like horror bloodfest kind of thing that he had created.
Awesome.
And so that was the first demo of this crypto system, was ultra secure encryption, probably a movie that didn't see wide distribution. So, but that was a fun story. But yeah, through that, I think Paul was projecting that there's only going to be a few more generations of optical disk, and hard drive capacity is growing. There was LimeWire and BitTorrent and all this stuff, people sharing movies. And so, Hollywood was as scared as the sort of recording studios were in the late 90s. So they wanted to figure out like, what are we going to do next? And there was probably going to be one more disc standard after DVD. We didn't know what it was going to be, but at the time it was the DVD Forum that was trying to standardize something. So, we joined the DVD Forum and started working on designing like what kind of system would work for these kinds of things. And the general idea was to kind of take what we had learned in satellite TV and build something that's more standardized to be able to have each disc, or each title at least, have its own protection scheme that changed over time. The goal was always focused on, let's preserve the release window. You've got 30 days to make your money back on your DVD. And at that point, whoever is going to buy Big Mama's House 18 has already bought it, and you're not getting long residual sales. I mean, Disney was kind of a custom case there because they have things that last forever.
Yeah.
But like every other studio was like, give us 30 days and we've made 90% of our money on that. And that's good enough. Everyone understood that you couldn't have perfect security forever.
Which is great, because there are some systems in some organizations where they're like, no, it is indefinitely has to be protected. And it's like, that is a lot of investment for not a guaranteed outcome. And like, so having the clarity to be like, we just need it to be protected for a finite amount of time is great.
Absolutely. I mean, when people got it, they would say that. Sometimes there were some studio people that wanted perfect security forever, and we try to talk to them about how that wasn't possible, and set expectations. But we started working on this design of the system. It was called self-protecting digital content, and the idea was each player would have a virtual machine that was standardized, and that was just an execution environment. You build your own copy protection in software for that one disk that you're shipping, and it would do whatever you needed to do to counter the known attacks at the time.
Okay.
So it was paired with like a key tree as well. It had the player had signature keys; it could sign stuff for you. Had encryption key tree, so it could be revoked if the specific model or serial number was compromised and the keys were leaked. And then the software could also do some things to try to counter whatever the pirates are doing. And the thing that took a long time to convince people of, but was how we wanted to sort of fight this battle, was people would always come up with a one-off attack. They'd say, well, what if I can, use side channel analysis and get hardware keys out of a Sony player or whatever, or what if I can reverse engineer the software player and get the keys out of it? And we're like, yes, that's going to happen. But people have limited resources who are attacking these systems. They're going to pick their favorite thing. Maybe they're really good at Windows and reversing there, or maybe they've got, hardware ability and they're constantly probing DVD player, like hardware DVD players. So for each attacker, there'll be their own specialties and they'll go for the weakest part that they can do, but that can also be targeted to slow down those attacks. Mm-hmm. So for example, let's say you extract keys. Well, you can do operations with the encryption keys. And if you're in an emulator, you'll be running on the same keys as, meaning if you're running an emulator for like a hardware player, you'll have the keys saying, hey, I'm a model 1000, whatever, but the timing is different in the emulator, or it's because you're running on software on a PC or things like that, or ripping software. The events that the user is pressing button events are coming in at a different rate or different synchronization with various events happening within the computation environment. So all these things could be detected as differences between someone trying to attack you as an emulator and the actual real thing. And all you needed to do is you didn't need to anticipate every way someone could do this. You just needed to be reactive and a little bit proactive in countering what you think their next move might be. Mm-hmm. And so that's what we did. So we built a system that had these capabilities that we call it renewability, that each time you had a new disk, you could do something different. And it was really interesting when it came out because we had no idea which routes attackers would take. And sure enough, ripping software came out. And, first people sort of targeted software players by extracting keys from those, and software players, because PCs had to be online at least some of the time, you could require more frequent updates, so of the player itself. Mm-hmm. So you could just be like, rev your keys, software player every month or whatever it is with a new update to it. And also patch a few ways that we think they're reverse engineering your software. And for hardware players, like once that was starting to get countered, hardware players were the new target. And people found a few models where they could extract the keys relatively easily from the hardware. And they started using those, but those were really constrained environments. And so it was really easy to characterize timing differences and implementation differences of servos and stuff like that. And you seek here and suddenly you're just instantaneous seek. And one of our big updates we did that I had a lot of fun with was, there's a bunch of titles coming out for the holiday season. And it's like, okay, that's where a lot of money is going to be made. So we want to do the best thing we can do. So we built something a little bit similar. This was sort of my baby, which was a randomized hash function that was built from both the user. There's a Java side that runs BDJ, which is the like the menus and the animations and stuff. Yep. And then there was the BD plus VM, which is sort of the content protection. And both of them are running at the same time. There's communication channels between them. So I was like, okay, I'll build a hash function that half of it's implemented in Java and half of it's implemented in C. And it's randomly generated by a code generator that each round of it, and they interchange between rounds of this hash function, their values. Uh-huh. And each one is hashing in just a ton of stuff. And we reverse engineered a bunch of the software players. We had gotten some of the characteristics and timings from the hardware players. And it would pick, for each player family, it would pick a hash function to execute and decrypt it using the keys for that device and just execute it. Be like, okay, the Java side would like throw an exception of a particular kind and then walk the stack trace in the exception and grab strings out of it and hash those and, add some numbers together and divide by 0 and check exceptions out of the stack of that. And on the C side, it was, analyzing timings of response times of the Java side and all this stuff was being fed into it. And there were what we called chaff which were just like garbage things, which weren't actually useful. We were checking. And it would always be the same on a particular model player or whatever, or it wouldn't vary very much. But there was just like, a dozen of these checks in each side with custom hash function built around each of them. And then the value would be used to decrypt the next chunk of stream in the audio and in the video. And so this system like really took them a long time to implement because they had to pull in a whole JVM. They had to re-implement all the class libraries and all this. They had to get it right and figure out what we were checking for. And at each title, we just roll out new fingerprints that were fingerprinting new aspects of the behavior of these players. And that took them a long time. I think it took them, I don't know exactly, maybe 30 to 60 days to crack that one. Mm-hmm. And at the time we had some knowledge that they were getting early advanced copies of these disks with the protection on it. And we're getting a head start on cracking them. So
that does sound like it's a lot of work to fingerprint each new system/title to update the parameters of how to generate these bespoke hash functions that you need to do the key derivation. So where was the trade-off, the marginal trade-off point between how much work it was to re-fingerprint the parameters to generate these hash functions versus how much it bought you against the crackers?
We had standardized the test disk that we'd play in a bunch of players, and it would print hash values to the screen of various fingerprints. Okay. So each time players were being, even the hardware players would have an update, and there was a way to do a firmware update from the disk as well. So over time, sort of hardware players were staying up to date. So we could rerun the test disk on new versions of it and characterize new things. So it was a little bit of work, but it wasn't terribly hard. The thing was the attackers were getting much better at just writing a bunch of code for emulating something and run the protected disk in their player and try to guess what we're looking for.
Got it.
And so it worked pretty well for a while. I mean, one of the funniest, the highest bang for the buck efforts was, and again, when you look at DRM, you're looking at a whole system. It's people, it's tools, it's techniques, it's money, resources, compute types, what operating systems people use. Maybe, someone uses VI or ZMAX, you can target them differently or whatever. But, in this case, we had some information that one of the developers had a big vacation planned of a ripping software. And so we had this inside tip and we're like, oh, this person's going on vacation. And we think that the junior developers who back up this person aren't actually any good. So we did a minor tweak of just shifting a few things around to an existing scheme that had been cracked already, and shipped that on the titles that were coming out during those summer months that this person was going to be gone on vacation. And sure enough, their forums lit up with I can't rip this, I can't rip that. And then the junior developers got on the message boards and they're like, oh, it's been a major change in the software. We're working on it really hard. And I think we got 30 days out of that one. And it was the tiniest, easiest change, but they didn't know what they were doing. And we knew this person
wild, because wasn't
going to get back to it.
I wouldn't have imagined this sort of counterintelligence tack to your attackers and then countermeasures based on your intelligence incoming about just this extreme cat and mouse game, but in the Soviets versus the CIA style of that's wild.
That was the fun thing about cryptography research, was everyone played for keeps. I mean, everybody was doing everything they could to be successful, and we didn't leave any stone unturned. When you look at these, like I said, these are ecosystems. You're working with people and tools and techniques and resources. And, it could be as simple as buying a PC for, somebody who works on a wares firm or whatever like that. And, they'll tell you stuff. And, so there's lots of interesting ways. If people, when people are dealing with fraud, for example, in the credit card industry, if they're not really sort of knowing the attacker environment and adapting to it, they're leaving a lot of capabilities on the table.
Yeah.
Do you think that this was this a differentiator between Blu-ray and HD DVD when that battle was happening, or is this kind of independent of all that? Was this were studios coming and being oh, we'll do Blu-ray because we think that their copy protection is better, or was that not even part of that discussion?
It was very interesting. There were a couple studios that it mattered a lot to, and there were others that it didn't seem to matter at all to, and it was all horse trading. It's in fact, I think there was one executive in the studio who even had some IP in some kind of part of the laser system of some existing DVD red laser system or something like that. And so they were going to make money regardless. And so, there's things like that where the incentives weren't always aligned. We kind of approached it, I think, a little bit naively in thinking that studio, if you can offer something that's better, studios will all get behind it. Just be we want this to be better. But a few people, it was well, if there's any kind of cost to this at all, if it's not completely free, we're not going to do it because we're about the lowest margin possible discs. And we want to get the production costs lower. We don't want to do any custom animations for our menus. We just want to ship this stuff constantly. And others that cared a bit more. It offered value, but the value was sometimes hard to define because, if you get 30 days of protection, but the attackers got the disk 30 days early, it looks like you had a 0 day and you didn't offer any protection for the release window. So it's one of those things where you have to get it right at all stages of production to actually show value.
Yeah.
So I think it was successful in particular instances, but overall as a scheme, it was very complicated and unwieldy and hard to keep all people rowing the same direction in terms of the industry.
Yeah.
Well, if I remember right, I think Blu-ray was considered to be like the better technology. So this time around, I guess the better technology did win out. Shipping code on the discs to the VM, though, that's very clever.
Thanks. The actual like HD DVD versus Blu-ray, from the inside, it looked very different from how it looked on the forums in the mid 2000s. On the forums, it was like, oh yeah, Microsoft is pushing HD DVD and this and that. But Microsoft didn't really care that much about HD DVD. It was to them a stalking horse to prevent Sony and mess with Sony's efforts on the PlayStation 3, which they really cared about. Because Microsoft at the time really wanted to own the living room. And at the time there wasn't like, the iPod was sort of going well, but there wasn't like, no one had mobile devices as the centerpiece of people's digital lives. It was a home server, and the home server was probably a game console for most people, or maybe a DVD player in this case. And so Microsoft was laser focused on, pun not intended, but focused on owning the living room. And all they cared about was, we need to be in control of that. And so anything to slow down, prevent people from getting in the way of the Xbox 360, they were going to do. So they actually pretended that they're like, we're going to join Blu-ray. They kept making noises about that internally. And like, if you just tweak this change or that change, we'll join. But really, they're just trying to throw up discord and slow down the effort as a whole. So I don't think anyone adopted Blu-ray because of the copy protection. It was more about like more disk size storage for that storage capacity, the ability to scale to more layers quicker. And the fact that HD DVD was kind of a Me Too format. Originally, it was going to be red laser, dual layer DVD discs. So it'd be really cheap. And so it was like, 9 gigabytes, dual layer with a high quality codec, the AVC, H.264. So the idea was you could do almost Blu-ray like things, but it wasn't as high quality. But then the studios are like, no, we want blue laser with whatever. So the DVD forum's like, okay, we'll do blue laser too. But, and Sony was originally part of the DVD forum with the blue laser technology, and then forked off Blu-ray because they weren't getting anywhere in the DVD forum. So all kinds of horse trading. And
I assume that's when like Microsoft decided they were just going to play interference, because that's the type of disc that the 360 used for games, was the dual layer DVDs. And that strategy seems to have worked, because for the first like 3/4 of that generation of consoles, the 360 dominated the PS3. And then they changed executives and absolutely pooched the next round. And then Phil Spencer has done an amazing job with that division after the next round of executives got booted.
I just remember by this time in our lives, right? Like I'd moved to San Francisco. We were actual friends by then. So I was talking to you like quite a bit while you were doing this work. And all I remember about this time period was your constant laments of being involved in the standards efforts.
It was awful. Yeah, absolutely. There were times when people would call an emergency meeting that you had to get on a plane to go to Tokyo for.
Oh my God.
And the whole purpose of the meeting was, we're going to vote on this one thing. And it was just to mess with people, to get them to have to drop everything and go to this meeting. And if you didn't show up, you're going to get voted out of the thing, because you only had a narrow margin of votes for you. And they're like, we got to get rid of this, 10-person company in San Francisco. And so if we do enough of these random meetings, eventually they won't show up to one, or they'll fall asleep or get to the wrong room or something, and we'll be done with this. So, yeah.
And it was Tokyo because Sony, and that's where all these devices were being manufactured, basically.
It was all rotating cities. It would be like, it's going to be I mean, my favorite part was when they held a meeting in Honolulu. And I was like, okay, free trip to Hawaii. That's not too bad.
Honey, I have to go. I have an emergency trip to Hawaii.
Exactly.
For one 15-minute vote.
Yeah.
That one was actually a more substantial meeting, but yeah.
The NCAA did this during COVID. They were like, the only way that we can vote on who's in the college football playoffs is to have an in-person meeting in Hawaii in November of 2020.
It's an emergency.
Nice. Well, mate, we have worked our way approximately halfway through your career of war stories, and while I would love to do a 4-hour episode of this show, I think what we're going to do is drag you back at some point.
Yay!
So I'm happy to come back.
Well, okay. Nate Lawson, you are one of my favorite people in the world. Outside of my actual family members, you might be my favorite person in the world. So
thank you.
I'm thrilled to have been able to talk to you on. This is awesome. So
Yes, thank you so much.
Thank you all. I really want to get to some of these other stories, which are really interesting.
So do we. So do we.
Okay.
Cool.
All right. Well, take care, everyone.
Security, Cryptography, Whatever is a side project from Deirdre Connolly, Thomas Ptacek, and David Adrian. Our editor is Nettie Smith. You can find the podcast on Twitter at SCWPod, and the hosts on Twitter at Durham Crustulum, at TQBF, and at David C. Adrian. You can buy merchandise at merch.securitycryptographywhatever.com. Thank you for listening.